Hey guys, in this video we're going to be talking about electronegativity and bond polarity. At the end of this we should be able to define electronegativity and look at the trends in electronegativity, know what bond polarity is, how it's related to electronegativity, use our Pauling electronegativity values to determine the electronegativity difference between two atoms, and from there determine if we have an ionic polar covalent or nonpolar covalent bond. So electronegativity itself is defined as the tendency of an atom to pull or attract bonding electrons towards itself. So we are talking about bonding electrons. So when we're talking about electronegativity, it only matters to things that make bonds. So if you look at the electronegativity values of things, and I'll point it out when we look at the actual table, you'll see that our noble gases, the things that don't bond, don't really have electronegativity values because they're not making bonds. You have to make a bond. And the scale that we use to show that tendency is called the Pauling scale. It's not the only scale that's used, but it's the one we're going to be using in this class. So it gives a value to the pull of the electrons by an atom in a bond. Okay, the values here are between 0.7 and 4.0. The smaller the number, it's going to pull electrons towards itself, bond itself. The greater that number, the more it's going to pull bonding electrons towards itself. Okay, larger value, greater pull. Now, when we're determining our bonds to look at where electron density is going, where those bonding electron or what that bonding electron density is going, we are going to use our electronegativity. Difference electronegativity is going to be the electronegativity value of atom 1 minus the electronegativity value of atom 2 with an absolute value. So you're looking at the difference between those two values to determine a lot of information about where those bonding electrons are going to go. Okay. The trend itself, when we're thinking about how this is going to change, it's going to be based on effective nuclear charge. So it's going to follow the effective nuclear charge. So as we go across our period, we're going to increase our electronegativity. So across the period, increasing that effective nuclear charge also increases our electronegativity. En, big E, big N, is my electronegativity. So electronegativity increases, and then going down a group, our effective nuclear charge decreases, so does our electronegativity. And as I said, if we look at our noble gases, they are basically zero because they don't do a lot of bonding. There are charts that show some electronegativity values for these because there are some bonds made with krypton and xenon and stuff like that. They're just not very common. And then we could see if we have like a pinkish color, we have a low electronegativity value, and as we get to blue, we get to a higher electronegativity value, and we see that increase as we're going across our periodic table, where our metals have very our non-metals have very great electronegativity values, which should hopefully make sense because our metals are going to give up electrons, our metals are going to take electrons in compound. So the thing that has greater electronegativity is going to pull electrons in, pulls them away because it has a low enough electronegativity. And we can look at that when we're looking at our electronegativity and bond polarity. So actually determining these values. So we think about bond types. We have two types. Ionic is the electron transfer. And covalent, electron sharing. And both of these can be seen by looking at our electronegativity value differences. So if we calculate the difference in electronegativity, we can predict the bond type. Okay, so if our electronegativity difference is greater than 2.0, so if we have a significant enough difference, we have an ionic bond. And then anything lower than that 2.0 threshold is going to be a covalent bond. But we have two different types of covalent bonds. So if we have electronegativity difference between 0.4 to 2.0, we have a polar covalent bond. So this is a bond where electron is not shared equally between the two atoms. So this is an unequal sharing of bonding electrons. And then if we have electronegativity difference that is less than or equal to 0.4, we have a non-polar covalent bond. And this is an equal sharing of bonding electrons. Okay? This, if we think about electron density of those bonds, we can see that with a pure covalent or non-polar covalent bond, the electron density is shared equally. And then with a polar covalent, we have electron density going in this direction. So we get a partial negative charge and a partial positive charge. We do not get a full charge because we are not transferring electrons. We are just shifting electron density towards the more electronegative atom. So this one would be more electronegative, and this would have a smaller electronegativity. Okay. Or it would be, we can say that it'd be more electropositive. So using our electronegativity differences, we're looking at that how electron density shifts. So an unequal sharing of electrons, sharing of bonding electrons, results in the formation of a polar covalent bond. So this is going to have a dipole. And a dipole is exactly that. It looks like a little pole. So we have a little bar magnet, a negative end, and a positive end. So this has no charge density. This has partial negative charge, partial positive charge, and then with an ionic, we have a transfer electron. We have a full negative and a full positive charge. So our polar covalent bonds, our atoms or molecules that contain polar covalent bonds, will have partial charges within. So molecules with polar covalent bonds will contain partial charges. And you can think of it like a magnet, like a little magnet. Where other things with partial charges or full charges will be attracted to it, and then things that don't have partial charges like our nonpolar covalent compounds will not be attracted to it and won't really mesh very well. So we can draw a bond dipole based on our electronegativity differences. And if there's anybody out there that is a physics person, this is going to be drawn differently than we would a vector, but it's the same idea as a vector. Okay, so a bond dipole is like a vector, but someone thought they'd be cute and wrote it in a weird way so it doesn't get written like a vector would. So a vector has magnitude and direction, and so does a bond dipole. But while our bond dipole, we're going to point towards the negative, a vector will point towards the positive. So again, same idea as a vector, but it's going to be pointed in a different way if you are a physics person. If you are not a physics person, just kind of ignore everything I just said. Okay, so the separation of charge in a polar covalent bond is shown as a bond dipole. Okay, so let's look at the following bonds and determine what the difference in electronegativity is and what type of bond is formed, and let's draw the bond dipoles if we have any. Okay, so a hydrogen atom has an electronegativity value of 2.1, and the other hydrogen is also 2.1. So our electronegativity difference here is 0, so this is a non-polar covalent bond. So no bond dipole. Okay, carbon-hydrogen. Carbon is 2.5. Hydrogen is 2.1. Our difference here is 0.4. This is right at that threshold. This is a non-polar covalent bond. So no bond dipole. A oxygen-hydrogen bond. Oxygen is 3.5. Hydrogen is 2.1. Our difference here is going to be 1.4. That is definitely a polar bond. So say polar covalent bond. And we would draw this bond dipole towards the more electronegative atom plus above the more electropositive atom, like so. Carbon-sulfur, 2.5, 2.5, giving us a 0 value. Polar, non-polar, covalent bond, no bond dipole. We could also do something like a lithium-oxygen bond. Lithium is 1.0, oxygen is 3.5. That difference there is 2.5. This is a ionic bond. So no bond dipole. We have electron transfer instead. Okay, that is everything. Just a little better. Sorry, I have a hard time saying electronegativity. Okay,